Our final section for Chapter 5 on control volume approach and continuity equation is about cavitation. Cavitation is a process that occurs when the pressure decreases dramatically within a flow regime, say in a pipe or around a propeller. There are a number of different applications. But this is something that engineers need to be very careful about if you're ever designing or working with flow problems, because it can be very devastating to equipment. It can damage equipment. So let's take a quick look at this. I'm just going to scroll all the way to the end of the chapter here. Been through a lot here, and here's our section on cavitation. And this just describes or shows some pictures of the results of cavitation. And you can see the devastation to some of these materials. Here's a small propeller, looks like from a boat, and we can see that there's this pitting that occurs here. This happens because we have very high velocity jets or streams of fluid that are generated around the blades of the propeller as it's rotating. And if the pressure is reduced, we get boiling, or we're reaching the vapor pressure, and so the fluid is basically starting to vaporize, and it creates bubbles. And when those bubbles collapse, again, when the pressure rises again and those bubbles collapse, they create very high velocity jets, which can damage materials. And then over here we can see the damage that was done inside over many years, a spillway in a dam. Looks like a tunnel to a spillway in a dam. For scale, you can see this guy standing here. So this is some pretty large scale damage that's occurred as the flow in the spillway was basically changed. The velocity was changed, and at times it would reach boiling. So if you can imagine a boiling fluid going through the spillway, that would be a pretty dramatic occurrence. So let's take a quick look at this. Bernoulli's equation, and I'm going to show you this in a minute, but Bernoulli's equation tells us that where we have high velocity areas, this is going to be accompanied by low pressure. So let's just take a simple situation where we have a flow. I'll just draw it here, that necks down, say it's a pipe. Up, I blew that. Let me try that again. We have a pipe that might neck down, and we're going to basically determine the velocity at point 1 and point 2 here. Again, in order to use Bernoulli's equation, we would have to do this along a streamline, so we're just going to assume that this is a nice symmetric drawing, which it isn't, and we're going to then apply Bernoulli's equation along the streamline. And I'm also going to note right away that the elevation of points 1 and 2 are equal, so we're going to just eliminate the height difference right now. So, and I'm going to use the pressure form here. So I'm just going to say P1 plus rho over 2 V1 squared is going to equal P2 plus rho over 2 V2 squared. This is the pressure form without the, again, we've assumed the elevations are equal, so they cancel. And so what we can see is if we rearrange this equation, if we're interested in the pressure difference, then we end up with V1 squared minus V2 squared, and that is actually multiplied by, rho over 2. But the rho over 2 is not so important here. But what I want to show you, I'm going to start a new well, I'll just do it at the bottom here. You can see that if V2 is much greater than V1, so as the fluid comes through this situation and it goes into this nozzle or this smaller portion of the tube or the conduit here, and it comes back out, the velocity is going to increase in here. If that's much greater than V1, then what we have is that P2 has to be much, much less than P1, because if V2 is greater than V1, notice the squares too, so this is going to go up quite fast. So as V2 gets much, much greater than V1, this is a negative quantity, and in order for this to be negative on the left-hand side, P1 has to be much, much greater than P2. So the problem, so we can see this is a direct application of Bernoulli's equation. And what happens is if we are above this, this line here and we have a fluid, and all of a sudden the pressure drops precipitously downward. Let me get a red pen here. And the pressure drops precipitously. If we reach this blue line, we will begin to develop bubbles or vapor in our fluid. And again, remember this was from chapter 2. These two slides actually show the same thing. This one is just to indicate this is on a linear plot. This one's on a linear log plot. These are factors of 10, each of these major divisions. And so we can see that this is exponential. So that's the reason why I have both of these curves here, just to remind you of that. But in any case, the bottom line is that if we're up here in either one of these curves and we rapidly decrease the pressure down to the vapor pressure, then we're going to have both liquid and gas existing simultaneously. So here's our little conduit with our neck down portion here, and we can see that what happens, we know that the flow is going to come through and it's going to accelerate through here. The speed's going to pick up here. But what happens is as the flow rate increases, the pressure decreases, and we have a high velocity region right in here. And so if this is not too bad, then we don't reach the vapor pressure. But on this pressure curve here, we can see that the vapor pressure is here. And if our flow goes fast enough that we lower the pressure to the point where we have the vapor pressure occurring, then we can have cavitation. And cavitation, here's a picture from the book that shows that cavitation can cause damage when the air bubbles implode in the liquid, again, as the water exits out the jet. So it's kind of a two-step process where the velocity comes in and it increases, the pressure decreases, the bubbles form, and then as they go back out here and the pressure rises again and the velocity slows down, these little vapor pockets basically implode into really high velocity jets, and they can pit the sides of whatever material you're containing the liquid in. So I encourage you to have a look at these links here on cavitation. And actually, Fisher Scientific has ways of avoiding this. So there's a couple of videos here that you can watch on YouTube. It's really good to look at some web links to see how cavitation occurs and to see some examples of the damage that it causes. It's a very important thing to realize when you're dealing with flow regimes in engineering, because of the extreme pressure decreases you can have when the velocity increases. Okay, thanks.